Hello, and welcome to another edition of the $10 Test Bench, where we try to find kits and electronics for the young players in the $10 or less region that they can use to learn electronics and do some experimenting and maybe take up an interest in a future career. Today we have what is billed. This little kit right here is billed as the ICL Function Signal Generator Module Sine Square Triangle Wave Output Kit GM, whatever that means. And for $2.54 delivered. Now, I can't mail a letter to China for that. I don't know how they managed to put these kits together and ship them here to the United States for $2.54. That just tells me that the Chinese government is subsidizing these folks in the hopes to probably bury us. And they're being successful at it, but you can't get something like this anywhere else. And what this basically is, if you look at this sheet here, is an 8038 ASIC. An ASIC is an application-specific integrated circuit. And that just means it's a little processor chip that can be programmed, and it's for a specific application. Once it's done in one. Now, they say it has excellent performance, small amount of resistive and capacitive components, can produce sine, triangle, and square waves. And then they tell you down below the description of the 8038 pin functions, and don't be thrown by 1 foot, 2 foot. They mean pin 1, pin 2, pin 3. So pin 1 or 1 foot and 12 foot sine wave adjusting terminals, pin 2 sine wave output, 3 triangle wave output, etc., etc. So basically they have an application specific chip here. So we're going to pull everything out of the bag. We will put this together and we'll do some quick experiments and see how useful this is. And by the way, this is supposed to cover the range of 50 kilohertz, or 50 hertz rather, to 5 kilohertz in 2 bands. So it should prove to be a useful little tool for doing some teaching and training. For our $2.54? Well, we have a small pile of parts here, a little potentiometer, some terminals, some screw terminals, the chip with some bent pins. We'll straighten that out before we solder it in. That's not great damage. We can, let's see if this is in focus here. We can straighten that out fairly reasonably. And a decent looking circuit board. It's nicely silk screened. Look at the glare off of the board here. And on the back side, nicely solder masked, and all of the solder pads are tinned, which is nice. That should make the solderability of this excellent. I'm very happy when I see tinned solder pads. You don't have to worry about oxidation of the copper and cleaning the board or using extra flux. The locations are clearly marked. It looks like all of the resistors are set up to be laid down. So following our normal procedure of starting with the lowest components first and working our way up, we'll start with the resistors. And for those who haven't watched the other videos, why do we start with the lower profile components? We can slip our resistors in and then lay the board face down and do our soldering. That way the resistors will be flat against the surface of the board. They won't be falling out. If you were to put, say, the potentiometer on first and mount that here so it was standing up above the surface, and then try to put your resistors in, as soon as you flip your board over, the resistors are going to fall out, and you're going to end up having to hold them and burning your fingers on the back side. Of course, Big Clive would laugh at that. He's got I think his fingers are made out of asbestos if you watch him do his soldering. At any rate, let's get some of the resistors put in here and we'll continue with the construction. Right, we have our components laid out for easy assembly. And there's only a handful of values here, so this is a fairly easy kit to build. It should go together quickly. We have 433K resistors. We have 1, 2, 3 10K resistors and one 200 ohm resistor. The capacitors, we have a 102, which is a 1 nanofarad. That's a 10 followed with 2 zeros, or 1,000 picofarads, or 0.001 for us old farts. Then we have a 103, which is a 10 nanofarad, and two 104s, which are 100 nanofarads. An LED, a switch, 1, 2, 3 potentiometers, one electrolytic, and I don't even know what the value is. It looks like 100 microfarad at 10 volts, and 3 little terminal connectors. So we'll get this thing started and pick it up from there. And while the soldering iron is warming up, I'll give you a quick view of what I mean by the lowest components, or the ones with the lowest profile first. Here we've installed all of the resistors in the board in their appropriate positions. Now when I put the board on the table, if I quickly flip it over, everything lays flat down on the ground or on the table, holds all my resistors in place, and then I can go ahead and solder these. And I hear the soldering iron ticking away. And then we can just simply go in, and without worrying about without worrying about the components slipping out of position, we can just go ahead and solder all the resistors in place, and then we can go back and trim all our leads. And you may notice that I'm using a rather heavy solder here. This is 0.062 diameter, or 1/16 of an inch. A lot of people would say I should be using a 32nd, but I find there's a little more flux in the 062 solder. It usually solders a little bit smoother, and a lot of times, well, plus I have a lot more of the stuff, but a lot of times I just grab this. I've been doing soldering for quite a while, and it goes pretty quick with this. If I'm doing something with very, very tiny spacing, I'll pick up the 030 and use a little additional flux. But for this board, the pretty open architecture, we shouldn't have any issues. Now that I've soldered all of those quickly to the board, we can flip this over and you can see all of my components are nice and flush with the surface. And we'll just continue in that vein. We'll put probably the capacitors next, because they appear to be the next tallest, and I've juggled all my parts around. The capacitors, the LED, the IC, and then I'll start putting the pots and the switches in, and we'll just progressively build up layers on the board. So we'll pick it up in a minute. Okay, next I'm going to put the integrated circuit chip in. Now I had considered using a socket for the IC, but at $2.54 for the whole kit, it hardly even justifies the cost of the socket. It would probably cost me $2 to replace the chip. If something goes bad, I'll just replace the whole board. Now when you get an integrated circuit, typically what you're going to find when you take it out of the package is the legs are split. Oops, let me pick that up off the floor. Okay, we've recovered our IC from the floor. Typically when you take an integrated circuit out of a package, the legs or leads are splayed to the side. I hope that's clear, not too much glare here. And you'll find that when you go to fit them to the board, they don't line up at all with the holes. Take your integrated circuit, lay it on a hard surface on its side, and very gently just roll it towards you a little bit. And I'm using a pair of pliers here so that I don't bend the top leads down. But if you carefully just roll it towards you, and do this a couple times until the leads are fairly straight, then the leads will be vertical, and you should find that when you pick up your board and put it in position, typically the integrated circuit will, and it's going to be difficult. I've got one side, it's got to come a little bit more. Never works on camera. I do this 100 times a week and it works perfectly every time, and when I try to do it for the film or for the video, I tell them I'm showing my age. Film. Your integrated circuit, there we go, drops right into the board. Then we can flip the unit over, lay it on its back because it's the next tallest component. Now when you're soldering a multi-lead component like this, don't just go down and solder all the leads, because if the component's not sitting flat when you're done, it's going to be very difficult to get it to do so. So I start with one corner here and one over here, two diagonal corners. Then when I flip it over and take a look, and if it's not perfectly settled, I can simply pinch the unit or pinch the device against the board, and by touching up a solder joint, I can get it to sit perfectly flat on the board. Then I can simply go down the line and solder all the rest of the pins, and my IC will be installed. Whoops, I just solder bridge. That's the danger of using solder that's this size, but that's taken care of. We'll just move right along and solder the rest of the pins. And I know somebody's going to go out there and say, oh, it wouldn't happen with the 031 solder. Well, it hardly ever happens with the 060 once you've done it a few times. And there we have it. The IC is on the board, quickly soldered. It remained nice and cool. We didn't overheat it. And we'll move on with the rest of our components. Well, we just had a little bit of excitement here, and I'm extremely sorry I didn't catch this on camera. I had just applied power to the board and was reaching for the camera to turn on the record button, and it went bang. It made a rather loud pop and smoke, and it was exciting for a second or two. I couldn't figure out what I'd done wrong. The chip, I looked up the specs on the chip, and the chip is rated for 10 volts to 32 volts VCC, or voltage in. The board has a marking for 12 volts. So I applied 12 volts and reached for the camera. However, the problem is right here on the board where you see this electrolytic capacitor, the capacitor supplied is a 100 microfarad 10 volt capacitor. Way underrated for the input of 12 volts. And as I was reaching for the camera, the steam pressure in the capacitor built to the point where it blew the bottom seal out and started to eject the insides of the cap. I have replaced it with a 100 microfarad of 25 volts, which is double the input of the 12 volt supply, and we shouldn't have any more issues. But if you buy one of these kits, be prepared to replace the capacitor. Now, these are cheap, you know, they don't cost anything. But it would have been quite a surprise for one of the young players, and they may not have been able to figure out what happened, thinking they did something wrong. You can't put a 10 volt rated capacitor, and it's clearly 100 microfarads at 10 volts. I hope I'm out of the light here. 100 mics at 10 volts on a unit designed to run on 12. Thank you, China. It woke me up. Okay, we have power to the board. You can probably see the red LED is on. It's always nice when they include an LED to show you that the board's powered up. Some people try to save a couple of cents and don't put it on their units. I think that's always a nice feature. The capacitor hasn't exploded. It has the proper voltage rating. On the back here, I hope this is fairly clear. Let's see if we can get the light. Yep, that should do it. We have our sine wave output, we have our triangle wave output, and we have our square wave output, and we have a common ground. I've put a loop of wire in there for my scope probe. The specifications for the chip claim that you can run multiple outputs at the same time. So in other words, all three of these are available at the same time. If you want to have sine, triangle, and square wave simultaneously, the chip will do it. I should say, however, this is unbuffered. So pay close attention to the specs on the chip. And the data sheet's readily available online, free. It's an 8083. The rated sine wave total harmonic distortion is 1% or better. The triangle wave is 0.01% linearity, so it's a nice little chip. It won't source much current, but if you want to drive something a little bigger, it's fairly simple to put a 1 transistor amplifier or a buffer after the board so that you can safely work with it and not blow the chip up. In fact, I would highly recommend that. In fact, we'll do that in a later series. We'll build a buffer and show you how much, or how to drive something, how much more current we can get with a buffer. We have our frequency set. We have our frequency range, high and low. And these, I'm assuming, are duty cycle. I haven't played with them yet. I haven't turned them. Right now they're in the center of their range. I'm going to hook up the oscilloscope and we'll see what we have. So bear with me. Alright, we have the unit set up on my venerable old Tektronix 2465B, and right now we have the sine wave output selected, and as you can see we can vary the frequency from its highest to its lowest on that range, and then we flip the switch, highest and lowest on that range, and I'll drop the scope back a little bit. So let's take a quick look at roughly what that frequency is. There's 92 hertz. Now they claimed 50. I can live with 92 hertz. That's just a matter of component selection on the board. I'm sure they've done some compromises on the board to allow sine, triangle, and square wave and get a reasonable range. But so let's call that 90 hertz just to round things off. And this range will take us all the way up to, from 90 hertz to about 712 hertz. Now this is rough. This scope's not a frequency counter. Those are just rough readings or average readings, if you will. They're not exact, and the scope I know is a little bit out of calibration. One of those things that's on my bucket list. Let's go to the high range, and the lowest frequency on the high range is roughly 400, let's call it 400 hertz, just to round things off, 429. And we'll go all the way up to the highest range, and I'll go up on the scope here so we can get a couple of, there we go. And that's about 6 kilohertz. Well, actually we can get it better than that. Almost 7 kilohertz. So a usable range. It would be nice if it went up to 10 or 15 kilohertz, but so be it. The unit functions. Now I do see distortion. They claimed 1% distortion, but I'm seeing a peak here and a peak here. Bear in mind they make sine waves out of the triangle wave, but the component selection on the board is probably such that it's not perfect. In fact, let's measure that distortion. We'll unplug that and bring it over here to my distortion analyzer. I should probably move the camera. Alright, we have a 1 kilohertz sine wave coming out of the unit into the distortion analyzer. We are on the 10% full scale range, and we're probably 3.2% distortion on the 1 kilohertz sine wave, which isn't earth-shattering. It's as we expected. We could see that peak on the scope. It would have been nice if it met its 1% spec that it has on the data sheet, but again, I'm sure some of this is just compromise on the board. of component values to give us a usable range and frequency, and allow sine, square, blah blah blah. They haven't gone to great lengths to equalize everything on the board. But for general use as a test oscillator, probably going to be fine. Again, a little bit over 3% distortion on the sine wave. And incidentally, I have played with the duty cycle and centering pots, and that's about as low as I can get it. If I play with this pot a little bit here and try to improve it, you see the distortion's going up, and the other direction it's going up. I can't get it to go any lower than that. We'll bring it back down here. Whoop. There's 3%, so there's a little improvement. And if I turn the other pot, oh, wait a minute, we are getting better. Maybe I just found the sweet spot. I was wrong once, then I found out I made a mistake. Ha ha ha. Yeah, the duty cycle pots are pretty touchy. You'd probably want to replace these with 10 turn pots if you really wanted to dial this in. But it shows it can be done. Come on, I overshot that way. When you're down at these levels, this thing is very sensitive. Okay, we almost had 1.5%. 1.8. So there you go, 1.8%. That's getting more respectable. I imagine if you replace these pots with 10 turn pots, you could probably meet the 1%. That's not bad for $2.50 something. 54 cents was it? I don't remember off the top of my head. Very, very real. Oh, my cheat sheet is over here. $2.54. I don't think you can go wrong for that price. Let's take a look at the other wave. All right, back over here at the scope, and I apologize if the camera hunts a little bit on the focus. It doesn't like to be zoomed very close. The autofocus gets a little bit finicky. If it's fully zoomed out, it's not a problem, but when you try to zoom in on something, the autofocus gets a little bit flaky. That's our sine wave. Let's take a look at our triangle wave. Oh, very clean. Very, very clean. Clean indeed. Very good looking triangle wave. Very nice. And again, we can sweep the frequency range with our triangle wave. Very nice. And we'll take a look at our square wave. And I think we've just gone off the screen here. Oh, there we go. Very decent looking square wave. No undershoot, no overshoot. I am impressed. Very clean. Very, very clean. Turn the intensity up a little bit here. This one. Just so it might be a little bit clearer on the camera. Nope, that might be blooming the camera. Maybe we were fine where we were. Yeah, that looks pretty good. All right. So there's our square wave. Now, we have our square wave. Let's play with our duty cycle and linearity controls here. Let's see. Yep, I'm going to have to play with my trigger, I think. Come on. Why doesn't it want to trigger on that? There we go. It appears the DC offset shifts, but you can see I can go from one side to the other, or go back to a 50-50 duty cycle. Now it won't exactly generate pulses, and again, that's going to be a compromise on the board so that you've got some range. Let's take a look at the triangle wave again. And we can change the slope on the triangle wave. We can't quite get a vertical sawtooth out of it. But not bad. Not bad considering. $2.54. I think I can live with that for $2.54. So, what have we got? Other than the exploding capacitor, which was kind of fun. I wish I'd got that on camera. For $2.54, I don't think you can go wrong. Now, it's never going to live up. Let's see here. I have a WaveTech function generator up there, but that's many, many hundreds of dollars, and that was thousands of dollars when it was new. And if I get this light out of the way up there on the top, and zoom in a little bit, I have a Heathkit sine square generator. Now those are exceptionally good sine square generators. Very, very low total harmonic distortion on the sine wave. Those can get down to 0.1% on the sine wave. Very, very clean. But those aren't cheap either. I've seen those selling for as much as $300, even though they're old and they're a Heathkit. It's because they're very, very clean. Not within the reach of the average young player. I will be looking around at the flea market to see what I can find, and I'll see if I can find a commercial sine square function generator in the price range, but I doubt I'm going to find anything for $10 that comes close to what we've got here on the screen for $2.54. So there you have it. Change the capacitor out if you buy this kit, or don't. Let it explode. It won't hurt anything. Then change it out. But do clean the board afterwards, because the liquid or the stuff that comes out of the capacitor is corrosive to circuit boards and wiring. So you'll want to clean the board up after that happens. Wash it down with isopropyl alcohol. I'm the Radio Mechanic. Hope this was of some use. We're keeping it short without experiments because we're trying to keep the videos within the attention span of the average viewer. We will be adding experiments at a later date. Please come back and visit. Give us a thumbs up. Please subscribe. And have a good day. We'll talk to you later. Bye-bye.